Welcome to the amazing world of solutes, solvents, and solutions, where everyday mixtures turn into scientific wonders. Have you ever stirred sugar into your tea and watched it disappear? Or mixed juice powder into water and created a tasty drink? That's not just kitchen magic, it's science in action. In this chapter, we will uncover how substances dissolve, mix, and form solutions. You will meet the solute, the substance that dissolves, the solvent, the one does the dissolving, and the solution, the perfect blend of both. From salty ocean water to fizzy sodas and even medicines, solutions are everywhere around us. So get ready to explore how tiny particles create big changes and why understanding them helps us in cooking, cleaning, and even curing. Let's stir up some curiosity and dive into the science of solutions. Let's dive into the fascinating world of solutions, where science and everyday life mix perfectly. A solution is a uniform mixture of two or more substances. Sounds simple, right? But the magic lies in how it works. In a solid liquid solution, the solute is the solid, like salt or sugar, and the solvent is the liquid, like water. So, when you stir sugar into your lemonade, you are actually creating a sweet science experiment. In a liquid solution, the one in lesser quantity is a solute and the one in greater quantity is the solvent. Think of mixing vinegar into oil for a salad dressing. Tiny drops of vinegar dissolve into the larger amount of oil. And guess what? Even the air we breathe is a solution. Here, nitrogen is a solvent, and gases like oxygen, carbon dioxide, and argon are the solutes. So every breath you take is a mix of invisible ingredients working together. From your kitchen to the sky, solutions are everywhere, quietly making life smoother, tastier, and breathable. Let's derive some science with two fascinating types of solutions, saturated and unsaturated. Imagine you're making a super sweet lemonade. You keep adding sugar and stirring until one moment no more sugar dissolves and it just settles at the bottom. That is a saturated solution. It is full, the solvent, that is water, cannot dissolve any more solute, that is sugar. Now, rewind a bit. When you were still able to dissolve sugar easily, that was an unsaturated solution. The solvent still had room to welcome more solute. Some real life examples are for saturated, it is a cup of tea with too much sugar, some stays undissolved. For unsaturated, a sports drink where all the powder dissolves smoothly. So next time you mix something and it vanishes into the liquid, ask yourself, is this solution still hungry or is it full already? Let's explore the science of mixing, where temperature, quantity, and chemistry come together to create different types of solutions. First comes the saturated solution. This is when the solvent says, I'm full. No more solute can dissolve at a temperature. Like when you keep adding sugar to cold water and it just sits at the bottom. Yep, that is saturation. Now, the unsaturated solution. Here, the solvent still has room for more solute. It's like a party with space for more gas, keeps stirring and it keeps dissolving. Next, let's talk about solubility. The maximum amount of solute that can dissolve in 100 ml of solvent at a specific temperature. It is like the solute's dissolving limit. And here is a cool twist. Temperature changes everything. For solids, solubility increases with temperature. So, hot tea dissolves sugar faster than cold water. But for gases, it's the opposite. Solubility decreases as temperature rises. That is why fizzy drinks lose their bubbles when warm. So, Whether you're mixing, heating, or cooling, solutions are full of surprises. Now let's explore a solution that goes beyond its limits, the supersaturated solution. Imagine you're dissolving sugar in hot water. You keep adding more and more sugar, and surprisingly, it all dissolves. You have now created a supersaturated solution, a solution that holds more solute than it normally should at that temperature. But here is the twist, it is unstable. Even a tiny disturbance, like dropping a crystal of sugar, can cause the extra solute to suddenly come out of the solution. It's like the solution saying, okay, that's it, I'm done. Some real life examples are making rock candy. You heat water, dissolve lots of sugar, and let it cool. As it cools, the extra sugar starts forming crystals, sweet signs in action. So, supersaturated solutions are like overpacked suitcases. Everything fits, but one little shake and things start spilling out. Let's break down the building blocks of matter: mass, volume, and density. Mass is the amount of matter in an object. You can measure it using a weighing balance, like checking how heavy your school bag is. Volume is a space an object takes up. You can measure it using a measuring cylinder, perfect for liquids like water or juice. Now, there is a cool part: density. It is a mass divided by volume. In simple terms, it tells us how tightly packed the matter is. So, a rock and a sponge may be the same size, but the rock is heavier because it is denser. Temperature effect. As temperature increases, density usually decreases. That is why hot air rises, it is less dense. And the pressure effect. It depends on the state of matter. Gases are most affected. More pressure can squeeze them into smaller volumes, increasing their density. So, whether you're floating in water or flying in air, mass, volume, and density are always at play. Let's explore how we measure density, even when objects aren't perfectly shaped. For regular objects like cubes or cylinders, it is easy. Density is equal to mass divided by volume. But what about irregular objects like a rock or a key? Here is a trick. First, measure its mass using a weighing balance. Then, find its volume by water displacement. Drop the object into a measuring cylinder filled with water and note how much the water level rises. That rise is equal the object's volume. Now, let's talk about temperature effects on solids. As temperature increases, solids expand slightly, which means their volume increases. Since mass stays the same, density decreases. It is a small change, but it matters in precision, science like designing spacecraft or bridges. Some real life examples of density are: oil floats on water because it is less dense than water. Iron sinks, but wood floats. Density decides who swims and who sinks. Helium balloons rise because helium is less dense than air. So, whether it is floating, sinking, or expanding, density is the hidden hero behind it all. And that wraps up our exploration of mass, volume, and density, the invisible forces that shape everything around us. We discovered how mass tells us how much matter is in an object, volume shows how much space it takes up, and density reveals how tightly packed that matter is. We learned how to measure irregular objects using water displacement, how temperature can make solids expand and change their density, and how pressure plays a role, especially in gases, from floating wood to sinking iron, from fizzy soda to helium balloons. Density is everywhere, quietly influencing how things behave. So, next time you drop something in water, feel the warmth of air rising, or open a soda bottle, remember you're witnessing science in action. Stay curious, keep exploring, and let the wonders of matter inspire your scientific journey. So, as I always suggest you, once after referring all the reference materials, please do read your textbook at least 3 times, uh, every 15 days once, so that the concepts will be registered in your mind. So it will be easy for you people to write the examinations with clarity. Thank you once again for all the loving children for your support, and please do follow my channel. And once again, thank you, and see you all in my next video.